All right, students, let's get into our fluid mechanics, chapter 12. All right. In order to understand fluid mechanics, you need to, of course, go back and review density to start with. You need to remember how we calculate density. Density is the ratio of an object's mass to its volume, mass per unit volume. Of course, we use the Greek letter rho. That's the Greek letter rho. And, of course, we write our density units. We write our density units in, I'm going to get it right eventually. We write our units in kilograms per meters cubed. Now, many times you may see it grams per centimeters cubed, grams per milliliter. Okay, we can write it that way, but typically the SI unit of density is kilograms per meters cubed. So remember, you need to always convert all your units to kilograms per meters cubed when you're working density problems, okay? Now, when we look at density, you say, well, we got objects of different sizes here. Do they have different densities? Their mass and their volumes are different. No, because they're the same material. Okay, so as long as an object is made of the same material and is at the same temperature, we got to be careful here, then they will retain the same density. So you mean to tell me, teacher, that I can actually change the density of steel? If you increase its temperature, guess what? The metal expands a little bit, and yes, its density will actually go down a little bit. Its density will change. That's why heating metals and then applying a lot of stress to the metal is not wise, okay, because you begin to change its characteristics, okay, unless you're wanting to change its shape. For example, that's when we put metal in a forge. We heat it up, so we weaken its properties, so we can do what? So we can shape it to a desired shape and then let it cool, and then its original properties come back, we hope, okay? All right, that's all part of heat treating, okay, the trick or the art of heat treating. All right, so they're the different sizes, different mass, but they are the same materials. Here's some examples of, or a chart of densities, common densities. Notice air, 1.2 kilograms per meters cubed. And of course, this is at 1 atmosphere and 20 degrees Celsius. Ice, notice ice has a very low density compared to water. Blood, aluminum, lead, and gold, 19.3. Now that's times 10 to the third. In other words, 19,300 kilograms per meters cubed, okay? So what about pressure? Now, we've already talked about pressure a little bit. We talked about it in the last chapter. That pressure is found by what? Taking the normal force, the force perpendicular, and notice this equation here. It's the derivative of what? Derivative of force with respect to area. It is a derivative, or you could actually look at that as a differential, I guess, if you wanted to. But it's the derivative of force, the normal force, with respect to the area that the force is applied to, all right? And notice that the units are newtons per meter squared, which is the Pascal. And yes, you need to remember all this, and yes, you need to write it down on your formula card, okay? All right. So, having said and done that, then let's look at pressure. So if we take an object here, and it's within a fluid and it's at rest, notice that the force on one side is equal to the force on the other, and so the fluid cannot exert any force parallel to the surface, since that would cause the surface to accelerate. Well, no, duh. If you take an object and place it in fluid and let it sit there at rest, within a fluid at rest, guess what? The forces are equal. So guess what? There's no net force on the fluid, okay? However, and of course you do need to remember this too, that pressure is a scalar quantity. It is a scalar quantity. The direction does not apply here. All we care about is the amount of force and the amount of area. All we're looking at is magnitude, the magnitude of the force and the magnitude of the area. So when we look at pressure at a depth, notice that we have to take in consideration what? The pressure of the fluid at the surface. That might be what you call atmospheric pressure, if you want to call it that, atmospheric pressure, the pressure at the surface of a fluid. Well, that's if the surface of a fluid, that means it's being exposed to atmospheric pressure, isn't it? Yes, okay. So when we have uniform density, the pressure, like say in the ocean or in a bucket of water or in a pool, then you have to take the initial pressure and add it to, notice, how do we calculate the pressure at a depth below the surface? Notice it is the density of the fluid times the acceleration of gravity times the height or the depth at which the object is in the fluid. In other words, if you have something like this, and there's a surface, and this is P naught or P initial, and let's say we want to know what the pressure is right here. Well, from here to here, that's height, isn't it? Okay, so this would be called final pressure, if you want to write it that way. Okay, final pressure. Okay, so the pressure at the depth of a fluid, notice this right here, each fluid column has the same height, so no matter what its shape is, the pressure is the same right there. No matter what the shape is, okay? Okay? Does everybody understand that? No matter what the shape is, the pressure here and here and here is the same, okay? Doesn't matter, all right? Now, notice this right here. The difference between PO and this is actually P final and P initial is PGH. We'll go back and look at your equation. Because look, watch y'all. If we say P final, and I'm going to put a final in there minus P initial, well, that's equal to PGH, isn't it? That's equal to PGH. Excuse me, rho GH, not P, rho. All right? Now, so Pascal's law basically says what? That a fluid, that when you apply force to a fluid, the pressure applied to that enclosed fluid is transmitted equally, or what we say here, undiminished, to every portion of the fluid and the walls of the containing vessel. So in other words, whatever the pressure is here, it will be the same over here. Okay? So the pressure is transmitted undiminished to every portion of the fluid and every wall of the fluid. And how do we find that? Well, again, pressure is equal to the force per unit area of 1 equal to the force per unit area of 2. And of course, you can set those up and find, in other words, if you want to find the force on 2, then the force on 2 would be equal to what? It'd be the force of 1 times the area of 2 divided by the area of 1, right? Okay. And you say, well, how can we do that? Because the pressure is transmitted undiminished. All right, nice little equation there you need to stick on your formula card, okay? Put that on your formula card. And remember, pressure is in what? The units are newtons per meter squared, which is a Pascal. 1 Pascal, all right? All right, so absolute pressure and gauge pressure. So when we say that the pressure in a car is 32 psi, which is equivalent to what? 2.2 times 10 to the 5th PA. We mean that it is greater than atmospheric pressure by this amount, okay? Pounds per square inch. So the total pressure in the tire is greater than the atmospheric pressure. So the excess pressure above atmospheric pressure is usually called what? Gauge pressure, okay? And the total pressure is called absolute pressure. So if the pressure is less than atmospheric pressure, as in partial vacuum, the gauge pressure would have to be negative, okay? All right, now they show you this. This is on page, I always turn too far. They talk about this on page 374, okay? So go look at page 374 and you can determine how do we calculate or determine gauge pressure, okay? All right, it's on page 374, okay? So Archimedes' principle, let's move on and talk about Archimedes' principle. The arbitrary element of fluid in equilibrium. So the forces on the fluid element due to pressure must sum to a buoyant force equal in magnitude to the element's weight, correct? Okay, so how does that work? Well, if you take the fluid element and replace it with a solid body of the same size, then notice the forces due to pressure are the same. So the body must be acted upon by the same buoyant force as the liquid element regardless of the body's weight. So how does that work? Basically, Archimedes' principle says that the buoyant force is equal to the weight of the fluid that is displaced by the object. So the volume of the object matters, because notice they said the body has the same size. In other words, Same size is volume, okay? So if you have two objects, regardless of their mass, if they have the same volume, then the buoyant force will be the same. Okay, why? Because the weight of the water displaced by the object is the same. Okay, notice I said weight of the water displaced, and that is dependent on the volume of the object that's doing the displacing. Okay, so a body immersed in water seems to weigh less than it does when it's in air. Okay, so when the body is less dense than the fluid, it floats, doesn't it? That is common sense. Of course, a piece of wood floats in water. Why? Because its density is about 0.4, isn't it? 0.4 compared to 1. Human body typically floats, okay, typically. Why? Because it's higher than 0.4, but it's still a little bit less than 1. All right, so when you look at these examples, these are examples of buoyancy, which was described by Archimedes in his Archimedes principle. So when a body is completely or partially immersed in a fluid, the fluid exerts an upward force on the body equal to the weight of the fluid displaced by the body. Okay, very important that you understand that. That is Archimedes' principle and what we call buoyancy, all right? And it has to do with the weight of the fluid. Now, surface tension has to do with this. If you take a particular, let's say, for example, water. Why does water have such strong surface tension? Well, because the molecules of water are attracted to each other, okay? All right? So when you have a molecule at the surface of a liquid that's attracted to the bulk liquid, this tends to reduce the liquid's surface area, okay? And so water has a very high surface area until you put a surfactant in there and break that tension, break those bonds, okay, and something called soap, and it, in a sense, loosens the water up, okay? All right, so what about fluid flow? When we look at fluids and how they flow through an object, say for a pipe, you have something called a flow line. That's the path that the particle is moving. And if you have a steady flow, then the overall flow pattern doesn't change over time. So, for example, if you turn the faucet on, you want a steady flow, don't you? Well, how does that happen? Well, because the amount of water pressure, you hope, is not changing, okay? So you have a steady flow, so the amount of water passing one point is the same at the next point, okay? So let's look at this. What about fluid flow? Now, when you have laminar flow basically means what? That the adjacent layers slide smoothly past each other, right here. You have laminar flow. Notice how they're moving along together. They're sliding past each other. However, here it becomes turbulent flow, and there's no steady state of continuous flow. So when we look at the continuity equation, or continuity equation for flowing liquids, notice that it's simply what? The area of one equal times the velocity of 1 equal to the area of 2 equal to the velocity of 2. Now, what in the heck does that mean? Well, basically what it's saying here, and that's cross-sectional area, okay? Cross-sectional, the A is area now. This is area, and that's cross-sectional area, And, of course, that V is velocity, okay? That's velocity. Then notice right here you have a large area with a velocity. Here the area gets smaller, cross-sectional area. Well, what do you think is going to happen to the velocity? The velocity is going to have to increase, folks. So let's look at velocity of 2 is equal to what? Area 1, V1 over what? A2. Well, if A2 goes down, guess what V2 does? It goes up, all right? It's inversely proportional, right? So if the volume, if the area at the bottom is less, then the velocity at the bottom is greater. Okay. Okay. Now this is all about fluid mechanics. You say, how do they get that water to? The water comes in at one speed and coming out the other to knock you down. Okay. Okay. Well, that's the continuity equation. Okay. Look at a fire hydrant. You got a what? 6 or 8 inch main coming in there, and then it's coming out of what? 1.5, 2 inch hole. You better believe the water is going to have a lot higher velocity. Okay? The water's coming out at a much greater velocity. And if it's coming out at a much greater velocity, you got a lot more energy. Okay? It's energy. Think about it. You have a lot higher energy. Notice that the volume flow rate, again, it is found simply by what? The change in volume over the change in time, which is basically equal to what? The area times velocity, isn't it? Okay, so there's you some more equations for your formula card. All right. Notice the continuity equation that we was talking about. Look, they're talking about honey here. Notice you've got a very large cross-sectional area here and a very small cross-sectional area here. Well, here the velocity's not moving so fast, but down here, man, it's a booking, isn't it? And if you've ever poured honey or syrup, you've noticed that as it begins to flow, it speeds up down here, but the cross-sectional area is much, much less, okay? All right. Now, let's look at Bernoulli's equation. Bernoulli's equation is basically due to the fact that the work done on a unit volume of fluid by the surrounding fluid is equal to the sum of the changes in its kinetic and potential energies per unit volume that occur during the flow. Do what? All right, so notice right here, this is energy, energy. All of this is energy. Okay, that is density times, that's pressure. Okay? All right, pressure. All right, notice right here. You say, why is that 1/2 there? It has to do with what? It's changes in kinetic and potential energies per unit volume. All right? Energy. So the pressure of 1 plus rho gy of 1 plus 1/2 rho times the velocity of 1 squared is equal to the pressure 2 plus the what? These actually come out to be pressures, okay? The rho times g times y of 2 plus 1/2 rho times velocity squared of 2. All right? So, basically meaning what then? That pressure 2 should be higher down here, right? Because why? Because velocity 2 is going to be higher. The distance at which it moved is going to be higher. So we should have a higher pressure, right? Right, okay. And then the Venturi effect, or what we call the Venturi meter. Have you ever wondered how in the world is the gas, you got a gas tank here on your lawnmower, and then you got your carburetor coming up and going here, and you got little needle valves and stuff. And I didn't really draw that right. Whoop, let me fix that. All right, you got a gas tank, you got the valve going down in here. Comes up, then it does this right here. You got needle valves and stuff. You got your motor over here. You wondered how in the world do you get the gas from here up to there? Well, out here is atmospheric pressure pushing down on the gas tank. Okay. Notice right here. Notice it tells us that the pressure is less at point 2. So point 2, the pressure at 2 is low. The pressure at 1 is high. Notice right here, this creates a vacuum. There's a vacuum right here. You create a vacuum right there. And so what does it do? It sucks the gas out of the gas tank. That's how it works. You create a vacuum. There's a vacuum created right here, y'all. It's called the Venturi effect. There's a vacuum created right here. Well, look, you've got a pipe connecting. Actually, we need to flip this over. We need to rotate this 180 degrees and let the pipe be going down in the tank. But you create an area of low pressure, which is an area of suction. Same thing, Bernoulli's principle applies to an airplane wing. All right? You create, notice right here, it's speeding up. The air is speeding up. V2 is high. V1 is initial, or 1 is low. All right. Here you have, and I did explain that, V2 here is high. Right there. It speeds up right there. It's lower back here. All right. All right. V2 is high. V1 is low. Pressure is low. Pressure 2. Pressure 1 is high. And so guess what? The plane, the air sucks the plane off the ground. It sucks the plane off the ground. That's how it works. That's Bernoulli effect, okay, or Bernoulli's equation. It's the Bernoulli principle, okay? All right, I pray this has helped you understand fluid mechanics.